Right, so we have rotational inertia of a point mass is given by mr squared. The two bunnies are of equal mass and they're on a merry-go-round. The bunny Clyde is a distance r away and the bunny Bonnie is 2r from the center. The merry-go-round is rotating at a constant rate, completing one rotation in the time t. Like period, right? The time it takes to go one, oh, I guess it's going this way, one rotation. I want to find the ratio of Bonnie's angular velocity compared to Clyde's angular velocity. So remember, the definition of angular velocity is the rate at which the angle is changing, the rate that the angular displacement is changing. If you look, as long as they're on the exact same disk, then they are rotating the same angle measure each second. So you should have said that the ratio of Bonnie's angular velocity compared to Clyde's was 1. I did ratio as like a fraction, so like the omega of Bonnie compared to the omega of Clyde would be 1. You could have said like 1 to 1, or saying that they're the same, so the ratio is 1. A lot of you guys use the equation, so on your equation sheet it gives you that t equals 2 pi over omega, which means that omega is equal to 2 pi over t. So as long as they have the exact same period, right, as long as they're turning in the same amount of time, they're going 2 pi radians in the same amount of time, so their angular speed has to be the same. I didn't use the equation, I just said they have the same angular velocity because they travel the same angular displacement in any an interval of time, which is saying this: they travel the same angular displacement 2 pi in any interval of time, specifically in the period time for one full rotation. The ratio of Bonnie's linear velocity to Clyde's linear velocity. So linear velocity is the rate that your distance or your displacement is changing. So they are definitely changing the same angle measure, but they are not traveling the same distance in every second. So you should be saying that Bonnie is definitely going faster than Clyde, because when Bonnie in one period, right, in one time travels this distance, Clyde only travels this distance, which is the same angle measure, 2 pi or 360 degrees, but not the same distance traveled, like meters. So you should be saying that the we're talking about linear velocity. So linear velocity of B over Clyde, you would get is 2 times greater, or you could say 2 to 1. The velocity of Bonnie compared to Clyde is 2 to 1. Where I'm getting that 2 from is, let's think, the linear velocity is V equals D over T. And if we're looking at T, then the distance traveled is just the circumference of the circle. So that would be 2 pi r. So the velocity of Clyde is just 2 pi r. Velocity of Bonnie is 2 pi radius, but its radius is 2r, twice that, over t. So some of you are like, oh, that's a factor of 4. Yes, that is a factor of 4, but this one has a factor of 2, so it's only 2 times bigger, which is what I want, right? 4 to 2 is just the same as 2 to 1. So it's going twice as fast because it has twice the distance, or twice the radius. So Bonnie travels a greater distance in an interval of time, because they're going the same angle measure, but a greater distance because Bonnie has a greater radius. Part C, find the ratio of Bonnie's angular momentum compared to Clyde's angular momentum. So angular momentum for something rotating is L equals I omega. So let's plug in for Bonnie and then for Clyde. So for Bonnie definitely has a greater rotational inertia because his mass is farther out from the center of rotation, even though the exact same mass. Bonnie has a greater rotational inertia than Clyde, and it tells me exactly how to calculate it. The rotational inertia of a point mass, in this case like a bunny, right, point mass, point bunny, is mr squared. So then for Bonnie, that would be m2r squared times omega, and then for Clyde, that's just mr squared omega. Now, I'm just going to leave it as omega because we already know that the omega of B and the omega of Bonnie and Clyde is the exact same, so let's just call it omega. So then the only difference between them is this factor of 2, but it gets squared, so the L of B over the L of Clyde is 4 times bigger. So this is saying that Bonnie has 4 times the angular momentum that Clyde does because it's twice as far away, and the rotational inertia is mr squared. So if you wanted to not just do math, you could say Bonnie has greater rotational inertia with the same angular velocity, so greater angular momentum. Okay. D, find the ratio of Bonnie's frequency compared to Clyde's frequency. Well, frequency is 1 over period, or I think the equation sheet says period is 1 over frequency, but that's the same relationship. So the frequency of Bonnie compared to the frequency of Clyde is just 1 because they have the same period. Or you could say because they have the same omega and like whatever frequency is 2 pi over omega, so it's basically all one relationship, just different variables showing the same relationship, but this would work just as well. Right, you are standing in the center of a spinning merry-go-round. You decide to walk from the center radially outwards. If you walk outwards like this, what happens to the angular momentum of the merry-go-round and the system? So if you are walking outwards, you are definitely changing the inertia and changing the angular velocity, but you would not be changing the angular momentum. So this is going to stay the same because there's no external torque, right? There is a torque between you and the merry-go-round, so there's no external torque. And I'll just put in parentheses, the torque is between you and the merry-go-round. I'm going to call it MGR so I don't have to keep writing merry-go-round over and over. So any torque is between you and the merry-go-round, which is going to be internal, not external. So total angular momentum must be conserved. Now, that doesn't mean that the individual angular momentums can't change. In fact, you at the center, right, you didn't really have any angular momentum because you were just at the axis of rotation. So the fact that you are moving out is going to increase your angular momentum and decrease the spinning merry-go-round's momentum. So we're going to look what happens to the angular velocity of the merry-go-round. So because the total momentum stayed the same, but you increase your rotational inertia. So by moving out, you increase the rotational inertia I. So the angular speed and the angular velocity must decrease. Because L total is constant. So a lot of times we like to just show this relationship really quickly. If this stays the same and this increases, this must decrease. So you would say your answer is that angular velocity would decrease. It's now going slower. Now back to what I was saying before, you know the total angular momentum stayed the same. Your angular momentum is actually increasing even though this is starting to slow down because your I is increasing because it's mr squared. So the more you increase r, the more up your I goes. And then yes, your omega does decrease, but the fact that the disk was spinning at a constant rate and now is going slower, the disk has to lose momentum, not the disk, the merry-go-round has to lose momentum, you gain so that the total stays the same. If you're on the edge of the merry-go-round and you walk along the edge in the direction of the merry-go-round, so let's say it's going around counterclockwise and then you start to walk counterclockwise. I'm going to start with you because I think it's easier to think about this. If it's already going this way and you also walk in that direction, then you are going to be getting faster. So your angular momentum will increase because you have a greater angular velocity now, because your walking velocity is added to the angular velocity of the merry-go-round. The same way when you're on like those walking, moving sidewalks at the airport, right? If it's already moving and then you also walk, you just go extra fast. That's the idea. So you have a greater angular velocity and you have the exact same rotational inertia because you're still at the edge, right? You haven't changed the rotational inertia. So you have a greater L. I'll say greater angular momentum. And then equation-wise, that would be L equals I omega. If this stays the same, but you increase this, then that means L must have increased. Now, you might be sitting there, wait, but I thought angular momentum is conserved. It definitely is in a system, right? So here, she got faster because there's a torque between you and the merry-go-round. So that means that the merry-go-round, if the total momentum has to stay the same and you increase angular momentum, that means the merry-go-round has to decrease angular momentum. And some of you were talking about like torque, like your feet are pushing against it. That is totally true. I just said it would decrease because the total L is conserved and the angular momentum of U has increased. So L of the merry-go-round must decrease to, well, I was going to say to be conserved, but we already said because L is conserved. The second thing is that you, like a lot of you were talking about like the torque, that totally works too. If she's walking along the direction of rotation, then that means that the feet are pushing against the rotation. So you also could say when you walk forward, your feet exert a torque against the rotation of the merry-go-round, which means that the merry-go-round's angular momentum would decrease because a torque is acted in the opposite direction. And then last part, we already kind of used this reasoning, but the angular momentum of U in the system would have to stay the same because there's no external torque. And then just making a note, the torque is between you and the merry-go-round. So merry-go-round. So that is an internal torque. Right? It makes one of you go faster, it makes one of you go slower, but then they still have to add up to the exact same total because angular momentum is conserved unless there is an external torque. If you are on the edge of the merry-go-round and you decide to walk in the along the edge against the merry-go-round rotation, so again, I'm going to start with mine because it's easier to think about. If you are on this rotating object and you start walking the other way, you are now going against that, so you are going slower than before. The same way if you're on that like walking sidewalk and then you turn and go the other direction, those are like velocities against one another, so you go slower overall. So your angular momentum would decrease because now you are rotating slower. If you have in the same rotational inertia, because you're at the same spot. So if you have L equals I omega, and this is the same, and omega decreases, that means L must decrease. And then I'm going to use this reasoning for the first part, so let's go ahead and say this one again. This would, for the system, of course, stay the same because there's no external torque. The torque is between you and the merry-go-round. That's internal, not external. So that brings us up to here. If you have the total staying the same and your momentum has decreased, that means that the angular momentum of the merry-go-round must increase because L total is conserved and the L of U has decreased. So the other one must increase because they still have to add up to the same number. And then if you wanted to think through torques, that works as well. If you are walking, let's say you are walking clockwise, that means you are exerting a torque counterclockwise. If it's already going counterclockwise and there's a torque counterclockwise, that's going to increase the speed, increase the angular momentum. Alright, number 3, a student sits in a spinning chair and is positioned, so they have rotational inertia I1 and are completing one rotation in 0.25 seconds. They reposition and are now completing one rotation in 0.4 seconds. What is the rotational inertia in this position? So I'm going to call it like situation 1 and 2. Here I know the period for this situation is 0.25. The period in the second situation is 0.4. My rotational inertia is just I1 here. My rotational inertia here is what I'm looking for. And then the only other thing you know about this is that momentum has to be conserved, because it was one situation, all they did was reposition, there was no external torque, so L1 has to be the same as L2, so these two have to be equal to each other. So I can say, okay, L is equal to each other. If L1 equals L2, I can use my I omega for each of them. It's just this is I1 omega 1, this is I2 omega 2, because L is given by I omega. I already know I1, right? I'm looking, it's I1, and I'm looking for I2, so now it's just figuring out, okay, what's my omega 1? Well, if you look at your equation sheet, we were given the period t. So if you look, t is 2 pi over omega, so when you rearrange, omega is 2 pi over t. So I'm just going to say omega 1 is 2 pi over t1, which is 0.25. And then omega 2 is 2 pi over t, but now t is 0.4. And now we substitute in. So I1, omega 1 we just said was 2 pi over 0.25 equals I2 over, times 2 pi over 0.4. Now I'm trying to get I2 by itself, and I want it in terms of I1, so that's totally fine that we plugged in I1. 2 pi can be canceled out, so you've got it on both sides, so I'm just going to put a 1 here, because it's not 0.4 now, it's 1 over 0.4. So if you have I1, 1 over 0.25 equals I2, 1 over 0.4, you can just multiply the 0.4 up, and that crosses off, right? Multiply by both sides, cancels out, and then you put that in your calculator, and you get 1.6 I1 is I2. And we could have said from the beginning that I2 is going to be a greater rotational inertia because it takes more time, so it's going slower. If it's going slower, that means it must have had a greater rotational inertia because momentum was conserved, so I knew that it had to at least be greater, right? If you had gotten 0.6, that wouldn't make sense. Okay, rigid rod is rotating about its end, has a rotational inertia of I. So this is the I of the rod. And the rod has a length L, like this, and a ball of mass M is traveling perpendicularly towards it with a velocity v naught. Rotational inertia of the ball is the ml squared, so this is I of the ball. And then the angular momentum of the ball with respect to the rod before the collision is mvl, so this is I of the ball, or not I, L of the ball, because it says angular momentum of the ball beforehand. It says, in one instance, the ball collides and the ball stops and the rod will keep going. Find the angular velocity the rod would rotate after this collision. We're leaving our answer in terms of m, v naught, L, and I. So we know that in any collision, momentum is conserved. So angular momentum beforehand has to equal angular momentum after. And the only thing that had angular momentum before was the ball. And then afterwards, the ball stops, and this goes off like, that doesn't look like an arrow. The rod will stop rotating, so then after, it's only the rod. And that's because the rod was 0 at first, and then after, the ball was 0. Alright, so then angular momentum of the ball beforehand, well, that was given. It tells me the angular momentum beforehand was mv, not L. And then angular velocity, or angular momentum of the rod after, well, the rod is rotating, so I'm going to use I omega. Careful thing here is a lot of people want to plug in ml squared. This is the angular momentum of the rod, so you want to do the I of the rod, right, to get the angular momentum of the rod, not I of the ball, because the ball is not moving, it's at rest. So when I asked to solve for omega, you actually just leave it like this, over I, because the I gave you was the rotational inertia of the rod, not the rotational inertia of the ball, ml squared. How do you think the angular velocity of the rod after the collision would be affected if the mass of the ball was increased? And I want you to explain without using equations. Now, when it says explain without using equations, that doesn't mean like don't think about equations, because you can absolutely look at this and be like, oh, a bigger mass will be a bigger omega. It just means you're not going to get points for that explanation. So use that to check and make sure you have the right relationship. And then now we're going to explain without using this equation. So definitely you should say that your angular velocity would be going faster, it would increase. And now our explanation would be, okay, well, why would a bigger mass mean that the rod goes faster? Well, a bigger mass means that it's coming in with more angular momentum. In the collision, this stops and gives all of its angular momentum to the rod. So if this comes in with more angular momentum, then the rod has more angular momentum after. And if the rod has more angular momentum, then it's going faster. So that's our reasoning without using equations. So the omega would increase because the ball now comes in with more angular momentum. So when, I'm just going to use L, so when the angular momentum of the ball transfers to the rod in the collision, the rod now has greater angular momentum, or L, after, so has a greater angular velocity. Because the you can put like a same I for the rod. Because if you keep the exact same I and you now have greater momentum, that means you have greater velocity, angular velocity. All right, how do you think changing the initial velocity of the ball would impact the angular velocity of the rod? So again, you can look and be like, oh, if this is bigger, so we know that omega would again increase. And it's basically for the exact same reasoning, because if the ball comes in with a greater velocity, the ball has greater angular momentum at the start. So when they collide, so then the rod has greater angular momentum after they collide and transfer. So then the rod has a greater angular velocity. Basically the exact same reasoning. Greater velocity means greater L at the beginning, so then same as before from there. How do you think the angular velocity of the rod would be affected if the ball had struck to the left of where it had initially struck? Because at first it said that it struck like at the end, like basically at the very, very end. If it now strikes instead of at the end, if it strikes right here, now it's not striking L, it's striking some distance less than the length of the rod. So now it's coming in with less angular momentum. So now if it comes in with less angular momentum, that means it transfers less to the rod, so the rod will go slower. So your omega would decrease because the ball now comes in with less angular momentum, so transfers less angular momentum to the rod, so the rod has less angular velocity. You also, again, can check with your equation, because now you wouldn't be putting in L, you'd be putting in some distance that is less than L, so then this would be less. Was I going to make any other? Oh, you also could make the argument here, because it's hitting, you could bring up torque. So here it's going to hit and stop, which causes some force to stop it. But now that force is exacted at a distance closer to the rod's pivot point or axis of rotation. So it has less of a torque, meaning it has less of a, less of a torque means less angular acceleration, so less speed after. But I find it easier to use the angular momentum. All right, in another instance, the ball, instead of stopping and continuing on, so before the after picture was this one was v equals 0, and then gave all of its momentum to the rod, which then rotated. Now it says that it's going to stick together, so it still has the same before picture, right, coming in like this, and now your after picture is that they're stuck together and they're both rotating with some angular velocity. So you should be saying that your angular speed would definitely be slower here. And the reason why is because, okay, well, the angular momentum of the rod comes from the angular momentum of the ball. Before, the ball gave all of its momentum to the rod. Now it's not doing that. Now it's only slowing down, giving some of its momentum to the rod, but continuing in the same direction. So now the two of them together add up to the ball's original angular momentum, which is way less than just the rod equaling the ball's angular momentum at the beginning. So, right for my explanation. We would say now, because it's continuing in the same direction, it's not giving as much of its angular, so I'll start writing. So now the ball continues in the same direction. Not in a line anymore, but it's still like the counterclockwise angular momentum. So it continues in the same direction. So it's not transferring all its angular momentum to the rod, only gives some of its angular momentum to the rod, so the rod has less L than before, so less angular velocity. Part 2, find the angular velocity. Will rotate after this collision. So I'm going to start with my L before equals L after. I'm still starting with just the ball before, but now I have both the ball and I have the rod after. So both of them are now moving. Before, it tells me what the angular momentum before, the mv naught, that's a given. The L after for the rod and the ball, well, they're both rotating, right? They're both moving in a circle, so this is going to be I omega plus I omega. Now, I want to make sure I use the I of the ball here, and I want to make sure I use I of the rod here. I don't need to call it omega of the ball and omega of the rod, because if they're stuck together, they're going to have the exact same omega, because they're literally stuck together. They have to be traveling together, have to be traveling at the same angular speed. Okay, and then if I'm trying to find this, well, first of all, the I of the ball was not a given, right? It says leave your answers in terms of MV, not L and I. I of the rod is given, it's just I. I of the ball was given up here. Rotational inertia of the ball was ml squared, so I'm going to replace this with ml squared omega plus I omega equals mv not L. Careful, do not cross off L's, because only these two have L's. There's no L to cross off here. I'm looking for omega, that's in two terms, so I'm going to factor that out. So, give it more room. So, let's write it over here. mv naught L equals omega. When I pull out the omega, it's ml squared plus I, and then we should divide this term over. So, mv naught L over ml squared plus I equals omega. And then we always want to check and make sure this at least makes sense, right? So this is going to be definitely slower than before, because before it was just mv naught L over I. I still have that, but it's over ml squared plus I, so I'm adding in to the denominator, which means I'm dividing by a bigger number on the bottom, so I'm going to get a slower omega, so that's good. It still makes sense that if I come in with more velocity, it'll go faster. If I come in with a greater distance away, that would make it go faster. The M is now a little bit trickier, because you're coming in with more momentum, but then you have, if you have increased the mass, you're coming in with more momentum, but then you're also making it harder to rotate, so that kind of cancels out. So at least this makes sense with the variable dependence. If in another instance the ball collides with the rod and bounces off with the speed of v naught, so it's still coming in like this, v naught m, this is my rod, but now my after picture is that this turns around and goes like v naught. And then this would of course rotate. Now compared to when it just stopped and gave momentum, when it bounces off, it's actually a really big change in momentum, which means it imparts a really big change in momentum to the rod. So the rod would actually be going faster than what we determined in part A. And the reason is because, again, change in momentum. Rather than just stopping, it stops, turns around, and goes the opposite way. So the ball has a greater change in angular momentum. And we know that momentum is conserved, so that means that the rod has a greater change in angular momentum. So it will have a greater speed. because it now has a greater L. And obviously the rotational inertia of a rod has not changed in that time. It might make a little more sense when you see the math. So find the angular velocity afterwards. So L of the ball before equals L of the ball and the rod after. Because again, after they're both moving. L of the ball before is mv naught L. Rod after is going to be I omega. Make sure you use I of the rod. Now we're not going to use I omega because when this bounces back, it's not rotating, right? This is again in a line. So it's actually the exact same as before, just changed directions. Now this is like the counterclockwise version, so I'm going to put minus v naught, mv naught L. It's the exact same angular momentum, m coming in at a distance L to the pivot with a velocity of v naught, doing the same, but now just bounce back the opposite direction, so put a negative sign there. If we're trying to find omega, we just add this over, which becomes 2m v naught L equals I omega. So then 2m v naught L over I gives me my omega, which compared to the original equation, which was the same but without a factor of 2, this is definitely faster. In fact, it's twice as fast because it has twice as big a change in momentum as before. Another way, instead of talking about change in momentum, you could say this starts off with some positive angular momentum, and then it gave it all to this side. So now when it turns around, now it has negative angular momentum. This will still have positive. So this has to be a greater positive number to add with a negative and still get the positive that you started with, if that makes sense. Or you can just talk about it, the change of momentum, like I said. And lastly, we've got a round cylinder with a rotational inertia of 2/3 mr squared. It's released from rest at the top of an incline, tilted at some theta, and has a height h. It's not on there. The cylinder rolls down the incline to the bottom, a distance d without slipping, so it's rolling without slipping. Rolling without slipping. And we want to first draw the free body diagram of the forces acting on the cylinder. It says with the vectors, like the arrows, originating at the point of application. So we did this in class last week. Basically, when we draw a free body diagram, we just draw like all the forces kind of coming from one point. But when it specifies, so in this point, it tells us draw the vectors at the point of application. That means don't just draw them all like coming from one point. Like where is the normal force acting on the object, etc. So I'm gonna just sketch in my ramp so that we have. Okay, cool. So we have 3 forces acting on it. Of course, we have gravity. Gravity is going to act at the center of mass, so that's going to come from the center, so that's easy. So I'm just going to call this mg. That's the force of gravity. Now, if it's sitting on a ramp, it also has the normal force. Now, the normal force is not acted at the center of mass, right? The normal force is where the ramp is pushing up. So your normal force should be coming all the way from the surface, pushing up, and this would be my normal force. And then, really shouldn't have drawn it quite so big because they were going to balance out, but that's okay. And then, lastly, we do have a force of friction, and we know we have a force of friction because it's rolling, right? If you just release it and there was no friction, there'd be no reason for it to roll. There's something pushing it, like causing a torque to make it roll. So then our friction always goes against motion. It's always parallel to the surface. So this would be my force of friction. Right here. Those are my only forces. Normal and friction occur at the surface. Force of gravity is coming from like the center of mass, which would be in the center. Part B asks if that same cylinder was now released at the top of an incline. It still has a height h, but that ramp is now frictionless. Will it take more or less or the same amount of time to reach the bottom as on this ramp? So now, still the exact same situation. It's just this one has friction, and this one is frictionless. So this one is, the big idea here is it has to do with rotation. If this one is frictionless, then you don't have this force, right? You just have the gravity accelerating it down. There's no torque causing it to rotate. If you notice, mg is acting at the center, so it can't cause a torque because its r would be 0, right? Torque equals rf. So you do have mg, but then your r would be 0, so then torque would be 0 for the force of gravity. The normal force can't cause a torque because it's acting through the radius, right, through the distance to the application, and it's r perpendicular to F. So if it's not perpendicular, this is again 0. So F of friction is the only force that causes a torque, so it's the only force that causes rotation. So if we don't have it, then that means that this one is not rotating. Whereas this one is rotating, it's rolling, right? It's rolling without slipping, it tells me. Okay, so then the one that will, or this one, if it's not going to rotate, that means it spends all of its energy, all of its potential goes into just the 1/2 mv squared translational kinetic energy, whereas this one has to spend some of its energy on rotation. So this one will definitely hit the ground or reach the bottom first because it's going faster on average. So now explaining all this, so the cylinder will take less time. This cylinder on the frictionless will take less time than the first cylinder because it's traveling at a faster speed. And then explaining how we know it's traveling at a faster speed, because I said explain thoroughly, so I want you to get into the details here. So we know this is traveling at a faster speed because it's giving all of its potential energy into just into just translational kinetic energy, whereas this one goes into both. So this is because it's traveling at a faster speed. This cylinder potential energy at the top transfers into all translational kinetic energy, 1/2 mv squared, and no rotational kinetic energy. And now we need to explain how do we know that this one has no rotational kinetic energy, whereas this one does. So I'm going to explain where we get this rotational kinetic energy for the first one. The first cylinder has the force of friction exerting a torque on the cylinder. And then your explanation is because the force of friction is parallel to the r, which is the distance between the force applied and the axis of rotation. It's a long parenthesis with a parenthesis in between. So that's just explaining how we know it's causing a torque, whereas the other ones are not. So because the force of friction is exerting a torque on the cylinder, it spends some of its potential energy at the top on rotational kinetic energy, so less on translational kinetic energy. So it goes slower than the second cylinder. There's probably going to be a more concise way I could have said that. Let's see what I said it on my other one. I said at first the force of friction exerted a torque on the cylinder which caused an angular acceleration. The gravitational potential energy the cylinder started with transfers into both translational and rotational kinetic energy. If there's no friction, there's no rotation, so gravitational potential goes into all KE translational, so it travels faster, so it reaches the bottom first. This was probably a little bit more succinct. Okay, study hard.